Assalamu alaikum. In this lecture, we are going to study the analysis of long transmission line through regress method. So if you remember from the last few lectures that I have given on the short transmission line model and medium transmission line model, what we were doing is that we were considering these resistance and reactances values as lumped parameters. Because the actual and the modeled results were not having much error, so therefore we were considering the lumped parameters in those models for the short transmission line and the medium transmission line. But as we consider the long transmission line, if we will consider the lumped parameters, the results are quite different and there is increasing error with the increase in the length of the transmission line. So therefore we have to consider the distributed parameters in case of long transmission line. These distributed parameters actually define the resistance, reactance and admittance value per unit length. So after every unit length, for example it can be meter or it can be kilometer, there is one resistance value which is in the impedance part of the transmission line, and there is a reactance value. So we have to model it in per unit. So we have a distributed parameters in the long transmission lines if we have to use that, because otherwise there will be a very big difference between the actual results and the modeled results. So as a starting point, we are considering a small portion of the long transmission line in which the portion dx, which is a small length of the line, is considered, and the impedance for that particular portion is z dx. Z is the total impedance of the line and the small portion length is dx, so the impedance of that small portion of the line is actually z dx. This is the length of the portion that is under consideration. Similarly, for the admittance value, y is the admittance of the whole line, right? So for the small portion dx, which is actually the length that is under consideration, the admittance value will be y dx. Before this portion, the voltage is V plus dV and the current that is entering into the segment is I plus dI. Similarly, after that segment we have the current I and the voltage V, and at the receiving end we have voltage VR where the load is attached with the transmission line, and at the sending end we have the sending end voltage VS. So now we can use this admittance value before the impedance as well or after the impedance as well, right? In the modeling of the transmission line, we can either place it before this impedance at this point or at this point. So that's up to you. The final answer will be same. So I will be considering this admittance value before the impedance value. So this impedance admittance value will be here, y dx. So now if we have to find the voltage across the series element, this is your series element, right? So if I have to find the voltage across this series element, the voltage will be dV is equal to I Z dx. The impedance of this series element is zdx, right? And the current that is passing through this impedance is I. So the voltage that is across this portion of the line is, or this small series element is dV. So from here I can write dV over dx is equal to IZ. This is our first equation. Now if we have to find the current through the shunt element, this is your shunt element. For current through the shunt element, dix will be equal to Vx plus dVx into y dx. The admittance value for this small portion or this small segment of the transmission line is y dx, and the voltage across this value is, the voltage across this admittance is V plus dV. So this is voltage into the admittance value. So this will give you the current that is passing through this branch. But we know that as this segment is very small, so this V dVx value will be very small. So we can consider that equal to 0. So this dIx will be equal to Vx y dx, and di by dx is equal to Vy. We can remove this subscript from here, right? So this is di over dx. This is your dv. So di over dx is equal to Vy. This is your equation number 2. Now if we have to find the solution for this differential equation, so first we will differentiate it with respect to x. This equation will become d square v over dx square z di over dx, and we know that di over dx from 2 is equal to Vy, so this will become d square v over dx square is equal to yzv. The solution of this differential equation will be equal to v is equal to k1 cos hyperbolic x under root yz plus k2 sin hyperbolic x under root yz. So this is the voltage value that you will get if you will solve this double differential equation. Now for this equation we have to find k1 and k2 values. But before that we should have another equation that will be representing the current. So to find that we have to differentiate this equation with respect to x, because from dv over dx we know that it is equal to current into impedance. So if I will take the differential of this voltage equation, that will give you an equation that is in terms of Iz. So after taking the differential, that will become dv over dx is equal to k1 under root yz sin hyperbolic x y z plus k2 under root yz cos hyperbolic x under root yz. So you just have taken the differential of this cos hyperbolic and differential of this sin hyperbolic. K1 and K2 were constant, so the differential of cos hyperbolic term is sin hyperbolic x under root yz, and this yz will come outside. Similarly for the cos hyperbolic term. Now we know that dv over dx is equal to Iz. So after solving this equation, we will get an equation that is for the current value, which is equal to under root y over z k1 sin hyperbolic x under root yz plus k2 cos hyperbolic x under root yz. So these are the two equations that we will be using further. This is your equation A and this is your equation B. Now we have to find the constant values k1 and k2, and we know that this distance x is actually the distance from the receiving end. X is the distance from the receiving end. So we have to apply the end conditions in order to calculate k1 and k2. For example, at the end of the line we have x is equal to 0 and the voltage at the end of the line is VR. V is equal to VR, and the current at the end of the line is IR, that is passing through the load. For the start of the line, X is equal to length of the line, because X is actually the distance from the end of the line, so it is equal to L, and the voltage is Vs, sending end voltage, and the current is Is, sending end current. Now putting these conditions in equation A and B, we will get equation A will become VR is equal to K1 cos hyperbolic 0 plus K2 sine hyperbolic 0. There was V term, and at the end of the line we have V is equal to VR. Here we have X, so X is equal to 0, so cos hyperbolic 0 and sine hyperbolic 0 will be the terms with K1 and K2, and this is equal to 1 and this is equal to 0. So we have our first value VR, that is equal to K1 constant. Now for equation number B, the equation will become IR, because the current at the receiving end is IR under root Y over Z K1 X is equal to 0 sine hyperbolic 0 plus K2 cos hyperbolic 0. So this is 1 and this is 0. So your IR value is equal to under root Y over Z into K2, or you can also say that K2 is equal to under root Z over Y into IR. So these were the values for K1 and K2. Now to calculate the sending end voltage, we have to use the sending end values for X, which is equal to L. For voltage it was equal to Vs, and for current it was equal to Is, right? So the equation for the sending end will be Vs is equal to VR cos hyperbolic L under root YZ plus under root Z over Y IR sine hyperbolic L under root ZY. And for Is, the equation will be Y over Z VR sine hyperbolic L under root YZ plus IR cos hyperbolic L under root YZ. So what you have done is you have find the values for K1 and K2, then you have put these values here. This is equal to VR and this is equal to under root ZY into IR. Now in order to calculate the sending end voltage, you have replaced V with Vs and this X value with L. So when you will replace these two values, you will get the equation for the sending end voltage and the sending end current. Now here we have one quantity that is under root YZ. This is gamma, which is known as propagation constant. And normally measured in per unit length. Similarly, we have under root Z over Y. This is known as characteristic impedance. Again, per unit length. And the last thing is Y over Z, that is known as admittance. So it is characteristic impedance, characteristic admittance per unit length. This propagation constant gamma consists of two parts, alpha and beta. Alpha is known as attenuation constant, and it actually measures the changes in voltage and current per unit length. Measures the changes in voltage and current per unit length. And the unit of alpha is Nepers per unit length. This beta is phase constant, and it actually measures the phase angle between the two segments. Phase angle between the electrical quantities voltage and current between two segments. What is the difference between the angle in the voltage and currents between the two segments, right? So if we are moving from one segment to another, so what is the change in the phase angle? That is measured by the phase constant, and the magnitude changes are measured by the alpha. The unit for the phase constant is radian per unit length. So these are the constant values that we should know about. So we have propagation constant that consists of two parts, alpha and beta. Alpha is the attenuation constant, beta is the phase constant. Attenuation constant measures the magnitude changes in voltage and current between the two segments, and the phase constant actually measures the phase angle differences between the two segments in both voltage and currents. Now we have a length term here as well as here. So we can write that L under root yz is equal to Ly dot Lz, and this will be equal to capital Y capital Z. So this is the admittance of the whole line, this is the admittance of the impedance of the whole line, and this is the length of the line. This admittance and this impedance is for a single segment that we considered in the start of the derivation. Similarly, under root y over z can be written as Ly over Lz, capital Y over capital Z. Admittance of the whole line, impedance of the whole line. So now when we will use these two derivations in the equation for the sending end voltage and current, we will get Vs is equal to Vr cos hyperbolic under root capital Y capital Z plus IR under root Z over Y sin hyperbolic under root capital Y capital Z. Similarly, for sending end current, the equation will be Vr under root Y over Z sin hyperbolic Y Z plus IR cos hyperbolic under root Y Z. So these are the equations that will be used in the numericals when you have to calculate the sending end voltage and the sending end current, and you are given the receiving end voltage and receiving end current. Now for the cos hyperbolic and sin hyperbolic terms, you can use the expansions. For example, the one expansion for cos hyperbolic term is 1 plus z y over 2 plus z square y square over 24 plus. Similarly, for sin hyperbolic, under root yz, you will have under root yz plus yz 1 by 2 over 6 plus. So you will have to use first 2 or 3 terms for these expansions to calculate the values for cos hyperbolic and sin hyperbolic terms. Or you can also use the sin hyperbolic formulas that are ex minus e minus x over 2. Similarly, for cos hyperbolic x, it will be ex plus e raised to minus x by 2. you just have to remember, when you are applying these two equations, you have to consider the VR value in line to neutral. Similarly, here you have to use the VR value in line to neutral. Thank you.